Okay, good afternoon, everybody. I hope you're all doing well. There are a lot of people at our campus because I think there is graduation ceremony of Paragon Primary International School. That's why grade 6 students are going to have graduation ceremony in the conference hall. Anyway, I hope you're all doing well. Maybe some of you are at campus, some of you are joining the class from your home. Last time in the class, we talked about introduction to systems of linear equations, and today we will talk about direct method for solving linear systems. Okay, so after that, I don't think we have time for 2.3, maybe about 2.3, we'll talk about 2.3 in the class, and after that, applications, and we have numerical method or iterative methods for solving linear systems. That's it. I'll try to cover everything maybe in 6 hours of class. And also about your quiz, I think we're going to have discussion about your quiz in the class, okay? So, and I hope you actually are aware of what actual progress you're making. See, the quiz result is really unsatisfactory. A lot of students, they did not understand very basic concepts. And if you just continue like this, guys, you may be in trouble, okay? That means that you will have to take this course again. As I told you at the beginning of this course, actually this linear algebra is quite different from calculus. In calculus, most of the things you're familiar and also you study similar things at secondary school or high school, right? That's why without a little bit preparation or practice, you can actually get the idea faster or quickly. But linear algebra is a bit different. The concepts are simple, but you have never practiced this before. That's why to get used to it, you need to practice. It requires a lot of practice until you gain some self-confidence, okay? Because when I was checking, grading your quiz papers, I noticed that very simple concepts, most of you, I'm not saying some of you, most of you did not understand, okay? Anyway, guys, I hope you actually learn a lesson from your result. I hope at least most of you. And you need to put some effort, okay? If you really want to learn something or at least get a good grade in this course, you need to put some effort and practice a bit more questions. So now in this section, we will look at a general systematic procedure for solving a system of linear equations. As I told you in the class, first we just considered a few of them, but simple ones, right? Okay, if you have like 2 linear equations in 2 variables, it's okay. Even if it is 3, it is 3. But now our purpose is, how about if we have like n equations with n variables or even less? And if we want actually to solve this equation with the help of computer, we have to transform our algorithm into computer language, right? How can we do that? Can we just write an algorithm for this step-by-step, actual systematic procedure? That is what we are going to study in this chapter. So this method is called direct in the sense that it leads directly to the solution if one exists. As you know, if you're considering a system of linear equations, right, we have 3 possibilities. One is it has a unique solution, or right, it has infinite many solutions or no solutions. So if you're talking about a system of linear equations with n equations and n variables, at that time, if it has a solution, actually our direct method gives us the solution directly. That's why it's called direct method. So keywords, let's have a look at this. Actually, you have to be really familiar or understand these words pretty well, because we are going to use them repeatedly in this chapter. Coefficient matrix, I talked about this in the class, augmented matrix and row echelon form, leading entry, elementary row operation, pivot or pivoting, row reduction, row equivalent, leading variable, free variable, rank of a matrix, reduced row echelon form, homogeneous system. These are the keywords that we're going to use throughout this chapter or even this section, okay? Now, again, let's consider this system of equations. As see here, we have 3 equations, right, and 3 variables. Now here, okay, x plus 2y plus z equals 12, and 2x minus 2y minus z equals minus 6, and x plus 2y minus z is equal to 2. Now, once again, how can I just write this in a form, right, that is easy to work with? Now, if I just actually first, after writing these letters or variables in alphabetical order, if we just write actually their coefficients, the coefficient of, what is it, coefficients of x, y, z in the first line, right? It is 1 and 2, 1. The second line, 2, -2, -1. Third line, 1, 2, -1. Now, augmented matrix, that means that we are adding one more column, that is the constant term, right? 12, -6, 2. At the time here, we have 1, 2, 1, 2, -1. The last column is 12 minus 6, 2. Actually, this is called augmented matrix. And simply, what is our matrix here? Our matrix is, this one is, again, just label this by, what is it, by A, okay? The matrix estimate, we just write it like this. And the second one is something like this. Here we have coefficient matrix, and we have constant, actually this term matrix. If we just augment this to the matrix, then it becomes an augmented matrix. Okay, so we are going to deal with this matrix. Now, let's talk about row echelon form. As I told you, to solve this system, we have to reduce this to staircase pattern or staircase form, right? That is like triangular shape. So not exactly, but usually also sometimes it looks like a triangular shape, but we call this staircase form, which is called row echelon form. So how do you define this row echelon form? A matrix is in row echelon form if it satisfies the following properties. Number one, if it has any rows which consist of only zeros, that is, any rows that consisting entirely of zeros, that row must be at the bottom of the matrix. And the second one, in each non-zero row, right? If we have any non-zero row, the first non-zero entry, we call this the leading entry, is in a column that is to the left of any leading entries below it. Okay, so now let's actually see this in examples. So the following matrices are in row echelon form. As you see here, there's 2, 4, 1, right? And these are leading entry. There's 2 and -1, and this 0. That's why if we have any zero row, it must be at the bottom. And after that, as see here, this leading entry, it must be to the left of the next leading entry in the next column, right? It's not like -1 and 0 to here. So this 2, so here, if I just draw stair, it must be like a staircase, right? And also here, what are the leading entries? These are the leading entries, 1 and 1 and 4. Why they are leading entries? They are the first non-zero entry in the row, right? In the first row, the first non-zero entry is 1, the second one 1, and the third one is 4. So actually, we don't have any zero row here. So any leading entry in a column, it must be to the left of the leading entry in another column, right? That is here, we have 1 to the left, this 1 to the left of this 4. And also the next one here, this is the leading entry, and this one is the leading entry. And we don't have leading entry here. Again, if you draw this, see here, it is, what is this, staircase pattern, right? So, and also the third one, also it is row echelon form. Here we have 0 and 3, and the first leading entry is 2, the next one is -1, the next one is 4, and next one is 5. These are the leading entries. And as its definition, in each row, the first non-zero entry, the leading entry, is in a column to the left of any leading entries below it, right? And that is to the left of any leading entries below this. Here we have -1, this 2 is to the left of this -1. Example 2, assuming that each of the matrices in example 1 is an augmented matrix. Write out the corresponding systems of linear equations and solve them. We are not going to solve all of them. Maybe we can just solve 3 or 2. Okay, and let me just label them. This one is the first one, A and B and C and D. Okay. So A, it says that assuming that each of the matrices in example 1 is an augmented matrix, right? Since it's an augmented matrix, the last column represents the what is it, constant terms. So the first one will be, what is it, 2 times x plus 4 times y is equal to 1. And the second term, that is minus y, is equal to 2. And the third one is just 0, 0, 0. It is this system of equations. Now from here you can find y is equal to -2. If y is equal to -2, substitute into the first equation, -8, take to the right hand side. It is 1 plus 8, 9, so that's equal to 9 over 10. And how about example B? What is the actually corresponding system of linear equations to this augmented matrix? So that is x plus 0, that's equal to, what is it, 1. The second one, y is equal to 5. And third one actually is equal to 0 is equal to 4. So this system actually, it doesn't have solution because of the third line, right? 0 is never equal to 4. And how about C? C is equal to, here we have x plus y plus 2z is equal to 1. And the second row, 0, 0, y, some z, so that's equal to z is equal to 3. And third row, only 0, so we don't have to write it. So that is the system, right? The actual system equations that corresponds to this augmented matrix. Now from here, z is equal to 3. So here we can find x plus y. X plus y is equal to 1 minus 6, that's equal to -5. Usually how this show the solution of this, how do you solve the system of here? Z is equal to 3, right? How about y? So we have two variables, one equation. So now if I introduce like this, y is equal to t is any real number, right? At the time this x will be -5 minus t. At the time the solution will be, let me just label the solution as a vector x, okay? X, it is -5 minus t. And the y is it's t, and z is 3. Okay, so I can just put it as a vector form. What is it? We know that it's just an equation of a straight line, right? Every point on the straight line, actually, it will be the solution of this system. Okay, so now we'll define another important concept here, elementary row operations, that we are going to use a lot to solve system of linear equations. So what operations are called elementary row operations? We have basically 3 elementary row operations. If you just remember again, to solve the system of linear equations, how to do that? We have to eliminate the variables, right? How can I do that? By first interchanging 2 rows or 2 equations, multiplying a row by a non-zero constant, and also add a multiple of a row to another row. Actually, these are called, or is it, elementary row operations. The first one actually with notation how to show that interchange 2 rows, that is, we're interchanging row I with row j. This means that we are interchanging 2 rows. Multiply a row by a non-zero constant number. That means we are multiplying row I by some constant, row I by k. And add a multiple of row to another one. That means that actually we are adding this k times ri, and we are adding this to rj. Okay, so that means that actually we are just multiplying i's row by k and adding this to the j's row and writing the new elements in row j. Okay, that's how we are going to perform these elementary row operations to solve the system of linear equations. Example, reduce the following matrices in echelon form. Okay, how do we do that? Let's start with the first one. Let me just say this is A. How do we reduce this? Of course, we can reduce this by, again, applying or carrying out elementary row operations over these matrices. The first one is, here we have 3 and 2 and 1 and 4. Okay, so the first elementary operation is, let me just interchange the first row with the second row. Okay, at the time here we have 1 and 4 and 3 and 2. All right. Next one is, let me multiply the first row. I can just write my operations here. The first operation is R1 is interchanged with R2. The second one is we're going to multiply R1 by -3. So -3 R1 and add it to R2. So that is, here we have 1 and 4, right? And -3 plus 3, it is 0. -3 times 4, -12 plus 2, it is -10. So now it is in echelon form. Okay, of course, echelon form is not unique and just one of them, but actually here we have reduced row echelon form. It is unique. We'll talk about this a bit later. Now, how about part B? In this, what is it, matrix? Again, here we have 3 and -2, -1. Here we have 2, -1, -1, and 4, -3, -1. So how can I bring this into row echelon form? To do this one, the first thing is I need to multiply, what is it? The first one actually by, what is it? 3. I should multiply this by -2/3, right? So at the time I have -3, and the added to the first row, to the second row, we will get zeros. So now I have to perform two operations. Number one is, just right here, okay? The first one is -2/3 times R1, and we have to add this to R2. The second one is, before this maybe, I should perform this operation and also multiply the second row by -2 times R2 and add it to the third row. Okay, so if I do so, let me just go a bit shorter. Okay, here we have 3, -2, and -1. Okay, first, if I do this operation first, and after that, this one second, -4 plus 4, it is 0. And this one is -2 times -1, it is 2, 2 plus -3, it is -1. And here we have also 2, 2 plus -1, that is 1, right? And how about the second one? Multiply the first row by -2/3 and add to the second row. So that's equal to 0. How about -2? Here we have -2/3 times -2, and we have to add this to -1, which is equal to 4/3 minus 1. That's equal to 1/3. Okay, and the next one is I should multiply -1 by -2/3. That is 2/3 minus 1. That's equal to -1/3. So here we have -1/3. Okay. So now actually we don't have to do that, but I can also do this in a much faster way. Every time I can simplify this. So now if I just multiply the second row by 3, at the time we have this matrix, -3, -3, -2, -1. Here we have 0, 1, and -1. Here we have 0, -1, and 1, right? So now if you add, if you multiply the second row by 1 and add to the third row, so here we have 3, -2, -1, 0, 1, -1. Here we have 0 and 0 and 0. So that is the echelon form of this matrix. Okay. Row equivalence. Okay. Matrices A and B are row equivalents. Actually, again, in math, before we understand this, you need to have some idea about what is it, what do we mean by equivalent, equivalent equations, equivalent variables, equivalent statements, and equivalent, equivalent, equivalent. Okay. Okay. So usually two equations are equivalent if they have the same solutions, right? And two inequalities are equivalent if they have the same set of solutions again. And how about two matrices are equivalent? Actually, we say row equivalent if we can actually transform matrix A into matrix B by applying a bunch of elementary row operations, or matrix B to matrix A by applying to a bunch of elementary row operations. Okay, at the time they are called row equivalent. So matrices A and B are row equivalent if there is a sequence of elementary row operations that converts A into B. Okay, usually one good method is a bit later, we will talk about a reduced row echelon form, because since reduced row echelon form is unique, we have to reduce them actually both to reduced row echelon form. If they actually are the same matrices, that means that these two matrices are row equivalent to each other. Otherwise, they are not. And for example, let's say here, this B looks in a more simpler form. Is it possible to convert this matrix A into B by applying a bunch of or a sequence of elementary row operations, right? To do this one, let's see. So this A is equal to, let me not rewrite this. Okay, let me just read a 1, 2, 3, 9, right? And here we have 2, -1, 1, 8. And here we have 0, 3, 0, -1, 3. Now see here, the first row, they are exactly the same. I don't have to do any change on the first row. And the second one is, how can I create 0 under this leading one, leading 1, 1 in the first row? To do this one, we should multiply the first row by -2, right? And add it to the second row. If you do so here, here we have 1 and 2 and 3 and 9 multiplies by -2, -2 plus 2, it is 0, -4 plus -1, that is -5, -6 plus 1, it is -5, -18 plus 8, that's equal to -10. And the third one, 3, right? Again, if we just multiply the first row by -3 and add it, so here we have 0, -6 plus 0, -6, negative 9 plus -1, that is -10. And here we have -18 plus 3, -15. Now I will multiply 1, 2, 3, 9, the second row by -1/5. That is 0, 1, 1, 2. And how about the third row? It is 0 and -6, -10, -15. Let me just keep it like this. Here we have what is it, multiplied by -1. Okay, that is, okay, let me just, okay, 6. Here we have 10 and 15. Now, if you multiply the second row by -6 and add to the third row, right, we will have, here we will have 1, 2, 3, 9. And this one is 0, 1, 1, 2. And the 0, it is 0. -6 plus 10, it is 4. -8 plus, no, -12 plus 15, it is 3. Okay. So now if you multiply this by -3 and add it, right? So it will be 1, 2, 3, 9. It is 0, 1, 1, 2. And -3 plus 4, that's equal to 0, it is 1. -3, it is -6, that's equal to, or did we make a mistake here? It should be actually 1 and 3, right? But if you multiply by -3, okay, -5, -5, -10, 1, 1, 2. So multiply by -3, -6, multiply by -3, -9, -10, multiply by -3, -27, -24. It should be -24. So after that, if you divide by -2, This one is 3. This one is 5. This one is 12. Okay, now minus 3 plus 3 is 0. Minus 3 plus 5. This one is 2. Minus 3 plus 12, that is 6. That is 6. So it will be 1 and 3. So as you see here, this matrix is equal to B. Since actually by applying a sequence of elementary row operations, we can convert A into B. So these two matrices are row equivalent to each other. Okay. And also actually these two matrices, they are row equivalent to each other. Maybe you can do this practice in school, or you can at school, or you can try yourself. Is it possible to reduce A into B by applying a bunch of elementary row operations? Okay. So theorem 2.1, matrices A and B are row equivalent. It says row equivalent, right? It says row equivalent if and only if they can be reduced to the same row echelon form. Okay, so actually we have already done this. Why? Because elementary row operation is convertible or irreversible. We can reverse that operation, because if you're multiplying by something, dividing or multiplying by the what is it? Like for example, let's say row, the first operation is, right, interchanging this Ri by Rj. So I can just reverse this operation. The second one is multiplying this by K, Ri. How can I actually obtain the original one? Multiplying by 1 over K, again, this row, right? And third one is actually we can multiply something, Ri, and add it to Rj. How can I reverse this operation? Multiply this the same, actually this Ri by K, K times Ri, and add it to Rj, we will obtain the same matrix again. So that's why matrices A and B are row equivalent if and only if they can be reduced to the same row echelon form. That means that actually suppose that here we have A, right? And I can, by applying some row elementary operations, I can reduce this to this matrix A. And also B, applying a bunch of elementary row operations, I can reduce this to R. So that means that now from R, right, I can actually construct actually a B from B, right? Since B can be reduced to R, R can be reduced, or using this R, we can obtain A. That's why if A and B are row equivalent, they must be actually, they must be convertible to the same matrix, which is in the form of echelon form, or which is in its row echelon form. Okay. Now let's start with the first method, Gaussian elimination. We have two different methods. The second one more powerful, actually shorter. The first one is Gaussian elimination. As you know, Gauss is, or is it Carl Friedrich Gauss, right? Was born in 1777 and died, I think, 1855 in Germany. He is a German mathematician, one of the most famous mathematicians in history. Anyway, that's why it's credited to his name. Write the augmented matrix of the system of linear equations. So if you're given a system of linear equations, how do you solve this? Using Gaussian elimination. So we need to write it, the augmented matrix of the system of linear equations, and use elementary row operations to reduce the augmented matrix to row echelon form. And using back substitution, solve the equivalent system that corresponds to the row reduced matrix. We have already done this in the class. Now we are going to do this one more time using those, what is it, terminologies. First, to do this one is saying that in the first step, we have to write the augmented matrix, right? What is the augmented matrix of the system? That is, if we have 1 and 3, -2 and 5. The second row, it is 3 and 5 and 6 and 7. Third one is, it is 2 and 4 and 3 and 8. That is the corresponding augmented matrix of this system. And the second step, it says that we have to reduce this to reduce this matrix to reduce what is it, echelon form, right? So by applying elementary row operations, we can do that. First, we have 1 and 3 and -2 and 5. So how can I create 0 under 1? Because this one is the leading entry. Multiply the first row. The first one is -3 times R1. We should add this to the second row. So if you do so, -3 plus 3 is equal to 0, -9 plus 5, that is -4, and 6 plus 6, that is 12, -3 times 5, -15, plus 7 is equal to -8. And the second one is, I multiply the first row by -2 and add it to the third row. So that is -2 plus 2, that's equal to 0. It's -6 plus 4, that's equal to -2. And 4 plus 3, that's equal to 7, because we multiply by -2, right? And the -10 plus 8, that's equal to, what is it, -2. Okay, 1, 3 minus 2, 3, 5, 6, 2, 4, 3, 8. Okay, we multiply by -2. It is 4 plus 7. Okay, nothing is wrong. So now if you look at this, the second row, right, is divisible by -4. Let me simplify this immediately. 1 and 3, -2 and 5. Here we have 0, multiplied by -1/4. It is 1. This one is -3, and this one is 2. So here we have 0 and -2 and 7 and -2. Okay, we will continue. The second step is, okay, we have the first row, we have nothing left here. The second row also, it is done. 0, 1, -3, 2. Now I need to create 0 under this one, right? This 2. What can I do here? Multiply the second row by 2 and add it to the third row. So here we have 0 and the 2 plus -2, that is 0. And 2 times -3, it is -6 plus 7, that's equal to 1. 2 times 2, 4 plus -2, that is 2. That's it. So we have reduced the given augmented matrix into reduced row echelon form. Now, after that, what is it? It says that we have to write the corresponding system, and by back substitution, we have to solve this. So the corresponding system will be x plus 3y minus 2z. That's equal to 5. And here the second one is y minus 3z. That's equal to 2. The third one is z is equal to 2. So now from here we can find y from using this. Right? So you can find y. What is y? 2 plus 6, that's equal to 8. And how about x here? Here we have 5 minus 3 times y. We just evaluate here. 5 minus 3 times 8 plus 2 times 2, which is equal to, it is 9. 9 minus 24, that's equal to -15. So x equals -15. So now dot, the solution of the given system is x, that's equal to -15, y, that's equal to 8, and z is equal to 2. Let me remind you one thing, okay, guys, again, here we are trying to understand the method, how the computer solves this. And in the question, I mean, in the quiz or exam, if I ask you using this Gaussian elimination method, solve it. If you use different method, you may get 0. Okay, we should try to understand this method, what's going on here. All right, so let's have break for 12 or 30 minutes. Okay, after the break, we will continue from here.